Hey guys, and welcome back to another AP Physics C video. This is going to be the start of a series I'm starting called Major Derivations because although I can cover as many free response questions I want, there are some major derivations that exist within mechanics and electricity and magnetism that every Physics C student should know and be able to replicate when asked. So I'm just going to go through a couple of those right now. Well, not right now. I'm going to go through one of them right now because I have post-it notes here for all of the derivations I'm going to do, but there's twice as many E and M derivations than there is mechanics. So when people say E and M is harder, it's for a reason. It's more calculus, more deriving, but mechanics has a lot less. So we're just going to start out here with deriving the rotational inertia of a uniform disk. And you might be thinking, well, this is not a disk. Actually, it is because rotational inertia is independent of the height at which the mass is put. Unless it's like some weird shape that looks like this. It's like a cone. Then that's a little bit different. But here, if it's at this bottom height, oh, and when this drawing, this is the central axis along which the disk will be rotating. So if there's mass that's here, the height that it's rotating about is still there. And if there's mass that's there, the height that it's rotating about is still there. So it doesn't really matter. The height is a rotational inertia, or dr, is independent of height, right? Dr is not rotational inertia. What I meant is the volume doesn't it's independent of height. The change in volume is independent of the height. So now I'm going to start my derivation knowing that. So we're going to know rotational inertia off the equation sheet is integral r squared dm, right? And you may be saying, well, no, isn't it mr squared? No, it's r squared dm because in this situation we have non-uniform small little dm's. Well, it's uniform, but we're working with dm's, not just a point mass. So we're not going to use mr squared. So now we're going to think, well, I know that the radius is r, and I know that the little radius we're going to integrate along is like dr. So I want to integrate in terms of dr. I want like r squared something dr. I want something like that, but I have dm right now. So let's work through this and try to get to dm. Well, we know the volume of a cylinder is pi r squared h. But as I said earlier, the volume dv, when I differentiate this, when I take dv dr, that will give me 2 pi r, right? And h, right? I'm going to consider that a constant because, well, guess what? It is a constant. So now I can say that dv equals 2 pi r d, 2 pi r h dr, right? But now you're like, oh, well, where's dm? Where does dm play into this? Now this is where the density is going to come in. I'm going to call the density rho. And I know the density is uniform, so I know that it's going to be mass per volume. But I also know that density is a little difference in mass, which is a little difference in volume, because density is a ratio. These two ratios will evaluate to the same. So now I can say that the density times dV is equal to dm. And you might be thinking, okay, so now I have dV and I know the density is m over v, so now guess what? I'm just going to sub in my things, and I know dV, I'm going to pull it. That's actually pretty bad. I'm going to pull it down here, m over v, 2 pi r h dr equals dm. Now I have something I can sub into that I squared equation, and it'll make some sense to integrate. So let's go ahead and do that. So now I'm going to get the integral m over v 2 pi r h r squared, because I'm pulling the r squared down because it was in the equation in the first place, dr. So now I'm going to continue by just taking out all my constants. M over v, actually it would be better to 2 pi, h was a constant and m was a constant over the volume. And now what's left in the integral is, that's a really bad integral, is r to the third dr. But now you might be thinking, this is an indefinite integral. How do I define this to be the right integral? Well, actually, it's not. We're going to put in our integration bounds now, because when we wrote, what we should have done from the beginning is we want to integrate from 0 to r. From 0 to r. Because the rotational inertia, the little dm's only last from 0 to r. Does that make sense? So we're going to go from 0 to r, because I want every little, sorry, I want every little dm that happens per dr from 0 to r, because that's the radius. So now when I integrate this, I'm just rewriting everything right now. That's a v, that's not r. I'm going to get r to the fourth divided by 4 from the bounds of integration from 0 to r. Now, big R, remind yourself, it's the radius of the actual cylinder. Little r is the radius function that we're integrating across, right? So little r is not equal to big R. I'm just about to sub it in, okay? So now, and if that doesn't make sense, please ask in the comments. So here now, I'm going to evaluate that right side, and I'm going to plug in, well, it's going to be r to the fourth divided by 4 minus 0 to the fourth divided by 4. Well, that just turns into 0, and now I get this monstrosity. H v r to the fourth over 4. So now I'm going to simplify that left side a bit because I know volume was pi r squared h. So I'm just going to sub that in. We're going to go 2 pi mh pi r, oh, and pi r squared h. And you might be asking, why didn't I put little r there if I put little r up there that time? Well, that's because I want the volume of the cylinder itself. This was volume as a function of radius. Now I want the volume of the actual disk. I want v disk. So that's where I'm going to sub that in. So pi r squared h, yeah, that was it. Okay. And now I'm going to multiply r to the fourth over 4. Now I can start canceling. Well, pi cancels, h cancels, and r to the fourth divided by r squared will give me r squared on the top. So this will become 2m, right? R squared, because here, this is what I just did, right? To get me that r squared. And now that's all divided by 4. And now I'll simplify that fraction, and that will give me 1/2 mr squared. And you've probably seen that equation before because that's the rotational inertia of a disk. So hopefully this helped, and that's how we got there. And yeah, this is the major derivation. And if you at any point you thought, well, how did you intuitively know that you're supposed to do this and that? I didn't. I watched another video by some other guy, and he taught it to me, and now I'm teaching it to you because these major derivations, they shouldn't be intuitive to most people. Some people like Gauss or like, I don't know, Lagrange, they might have thought of this intuitively. But now we're just replicating those steps. But some of these derivations, they might come intuitively. And as you keep going through these derivations and you keep watching these videos, at some point you'll be able to do it intuitively because that's the beauty of practicing this. So I hope this helped you guys, and I hope you guys all do well on the next E&M exam. Or not E&M, on the next upcoming exams in May. And I hope if you're watching this video post taking AP Physics C, you did well. God willing, we all get 5s. So yeah.